All right, welcome back to the video lecture series on chapter 3.1 from our textbook. So we were talking about election polling. So in the last presidential election, 2016, there was a poll of 1,007 likely voters were asked who they plan to vote for in the election. And given this information, so this is a Quinnipiac poll. And if you look over here, 50% of these voters said they were likely to vote for Hillary Clinton in the election. So we get a p-hat of 0.50. So this was done, I think, a couple months before the election. And now we actually know the population parameter. So this is a statistic. This p-hat comes from a sample. The parameter, the actual value after the election, we got Hillary Clinton got 48.2% of the popular vote of the election. So we would use a p-hat, or a statistic from a sample, is called a point estimate. So we get one value that is for a population parameter. And of course, point estimates will not match population parameters exactly, but they're a best guess given the data. And later in chapter 3, we're going to talk about moving from a point estimate to an interval estimate. That'll be later in chapter 3. So here we have some more results on, let's go back here, mid-October election polling. So if we look at Clinton, again, her actual election percentage, her population parameter P was 48.2. And look at this. This is an average of all these different samples. And that got pretty close to the actual value that Clinton actually received in the popular vote. So we're going to talk about sampling distribution. Think about, well, this right here gives us 1, 2, 3, 4, 5, 6, maybe 10 or so samples. And then if we take an average of all these sample means, then we get something that's maybe a little bit closer to the actual truth. Okay, so just to note, sample statistics will definitely vary from sample to sample. They will not match the parameter exactly. So what we want to know is, for given a sample statistic, what are plausible values for the population parameter? And then also, how much uncertainty surrounds the sample statistic? So these are questions that are going to follow us for the rest of the semester. And of course, we're going to talk about this. This depends on how much the statistic varies from sample to sample. If we think about varying from sample to sample, let's go back really quickly to this last slide. Look at all these different polls or samples that have Clinton at 50%, 47%, 43%. I think is the lowest one on the list, and then it goes all the way up to 53%. So there's some variability here of all these sample proportions. But taking the average of all these samples, we get a mean of the sample means that is fairly close to the actual value of 48.2%. Okay, so we're going to take a look at how we could get many samples to compute many different statistics. So if we were meeting in class, if this was a standard class, we might do this in class, but for this video lecture, we're going to kind of use StatKey to do the simulation for us. But suppose we want to know what proportion of Reese's Pieces are orange. If we look it up, Reese's, the manufacturer, claims that it's 50%, that half of the Reese's Pieces are orange. But one way we can check that is to check with random samples. So what I'm going to do that is to get a big box or a big container full of Reese's Pieces, and then take one random sample of 10 Reese's Pieces. Compute your sample proportion. So if you get 5 out of 10, 50%, that'd be your p-hat. If you get 4 out of 10, your p-hat would be 0.4, and so on. Enter on a dot plot. And we're going to repeat by taking many, many, many samples of 10. That is the idea behind sampling distribution. And so we're not going to do this right now on this video. Instead, I'm going to head over to StatKey. So I'm looking at StatKey, sampling distribution for a proportion. And we'll go over some of this in class, but also make some more videos of how to do this. For right now, I want you to think about, we're going to choose a sample size of 10. And we're going to assume that Reese is correct and that actually the proportion should be 50%. but I'm going to generate one sample. So this would be simulating grabbing 10 Reese's Pieces and counting how many of them are orange. And look at that, one sample of 10, we got 7 of those 10 are orange. So higher than it should be, but there's going to be some variability. We take another sample and we get 8. So two fairly extreme examples, 0.7, 0.8. And notice this little arrow maps the mean or the proportion of all the proportions. So it gets the mean of all these different proportions. So if I take another sample, I get another one of 7 out of 10. Then I got one of 0.5. Another sample, I got 1.3. 3 out of 10 were orange, and so on and so on. And I could have the entire class do this to get a bunch of information, or we could do many different samples over and over again. 100 samples, I got 240 samples, and then with simulation, let's generate 1,000 samples. So now we've taken 1,248 samples of 10 Reese's Pieces, and each of these plots out a sample proportion. So these are all a bunch of dots. Each dot represents one sample of 10, and then we plotted the p-hat, the sample statistic. And what do you notice about the distribution of these sample proportions? We get a fairly nice bell-shaped symmetric curve whose center is right at the population parameter. Okay, so that was what a sampling distribution looks like, doing all those dot plots. So sampling distribution is the distribution of sample statistics. What we just did on stat keys, a distribution of sample proportions, or p-hats. But we could do this for means also. And it's computed for different samples of the same size. So that's another key. We need to make sure we take the same size sample. In this case, we took 10 Reese's Pieces at a time. And the sampling distribution shows us how much the sample statistic varies from sample to sample. Think about the first couple samples, we got 7 out of 10, 8 out of 10. But as we did more and more and more, they tended to kind of veer towards the population proportion of 50%. So in the Reese's Pieces sampling distribution, what does each dot represent? Is it one Reese's piece or one sample statistic? Hopefully you said B, because it is B, it is one sample statistic. Remember, each one of those dots actually represents 10 Reese's Pieces. If the samples are randomly selected, and the sampling distribution will be centered around that population parameter. Again, think about the stat key simulation we just did. That bell-shaped center curve was centered at 50%. And then for most statistics, we consider the sample size is large enough. If the sample size is large enough, the sampling distribution will be symmetric and bell-shaped, as we saw in the last Reese's Pieces example. Okay, one caution though, if you take random samples that are truly representative of the population, the sampling distribution will be centered around the true population parameter. It's actually a mathematical fact, and it's one of the most powerful statements in all of statistics. But the warning we want to talk about is if there's a sampling bias. If you do not take random samples, there's a convenience bias or some other bias, you miss out on a subset of your population, then your sampling distribution may give you bad information about the true population parameter. I like to think about if you want to get the average height of a college student, but you somehow sample only the men's and women's basketball and volleyball teams, then you're going to have bad sampling. You're going to get your sampling is going to be much taller than the actual average. So we've learned about center and shape, but we really care what we're doing with these sampling distributions, this distribution of a whole bunch of different sample statistics, is the variability. How much does this sampling distribution, how wide is it? How much variability is there in the distribution? And our key question and answer from this section is we want to assess uncertainty of a statistics. We want to know how much the statistic varies from sample to sample. So this variability of the sample statistic from sample to sample, it gets its own name, and we call it standard error. So the standard error of the statistic, we're shorten it with an SE, is the standard deviation of the sample statistic. So the standard error measures how much the statistic varies from sample to sample. So it's not the standard deviation of one sample. That's not what this means. The standard error is the standard deviation of the sampling distribution of all the sample statistics. So keep that in mind. Standard deviation of the sampling distribution. That is the standard error we're talking about right now. So the more a statistic varies from sample to sample, think of the Reese's Pieces example we did. We had one that went up to 0.7, 0.8, 80%, and then we had a couple of 30 to 20%. Most of them were 40, 50, 60%. But the more the statistic varies from sample to sample, what's going to happen to the standard error? It's going to get higher. Again, the standard error measures how much the statistic varies from sample to sample. The standard error is a standard deviation just of the sampling distribution. Okay, we'll do one more question, then we'll break and finish this in another video. The standard error for p hat, the proportion of orange Reese's Pieces in a random sample of 10 is closest to, and here we have 4 options, and this is a different graphic than the one we generated. All right, and how do we get this? So 15%, we're looking for the standard error. So we're going to use the 95% rule. Where the 95% rule says if I've got a symmetric and bell-shaped distribution, and this is fairly symmetric and bell-shaped, 95% will be within 2 standard deviations. So down here it says 0.2 to 0.7. So if we look at this 0.2 cutoff right here, all the way to 0.7 cutoff, that gets you about 95% of your data. That looks approximately like 95%. So that's going to be within 2 standard deviations. So if we think about going from 0.2 all the way to 0.7, the difference between those two numbers is 0.5. But this would be 4 standard deviations, 2 above and 2 below. Oh, sorry, it's cut off down here. So we're going to take 0.2 to 0.7, find the difference between these two numbers, which is 0.5, but then we need to divide that by 4 because we've got 2 standard deviations below and 2 standard deviations above, and that's how we get the standard error to be 0.15. Or another way to think about it, if I have 0.45 is the mean, if I move 2 standard deviations below, that gets me to about 0.2, which gets me to that cutoff of where we're looking at the 95% in the middle. Okay, we'll look at some more examples of this in the next video.